I want to take a minute to talk about the forces that we have that give rise to uniform circular motion. We know that our acceleration for uniform circular motion is directed in towards the center of the circle, so therefore the force that allows me to move in a uniform circular motion has to be directed in towards the center of the circle. We know from Newton's laws that the sum of forces, let's get it bigger just so that's easier to see, the sum of forces is equal to mass times acceleration. So that means that if our force in the towards the center of the circle would be mass times our centripetal acceleration, which is v squared over r. So this is what we're going to use over and over and over again. Our net force is equal to m times v squared divided by r. Let's see how that shakes out in a few simple problems. Here we have the problem with a car on a level curve. So this car is sort of spinning, or not spinning, driving into the screen and then out of it. We are looking at the tail of the car as it's moving away from us. Imagine that. So the car's moving away, but it's going around a curve. The thing that actually keeps it from sliding on the road is friction. And if I don't want my car to slide left or right as it's going around the curve, right, as it's driving into the screen of my iPad, that means I have to have static friction holding me in. If I did not have this static friction, my car would be sliding on the road in this direction as it rounded the curve, and we're hoping that it's not going to do that. So that means that my force diagram is going to look like this. I'm just going to change this to R notation just because I stole this from another source. Sorry, Randy, if you're watching this video, my pal Randy Knight. Forgive me. I've got FG down, I've got our normal force up, and I've got my friction, that static friction here. And this diagram has reminded me that that is the force directed in towards the center of the circle. So that means that if I were to solve this problem using the given radius and the given coefficient, that would look a little bit something like this. If I want to know my maximum speed, well, I'm going to say, okay, my force is in towards the center of the circle. That means my acceleration is in towards the center of the circle. We've already seen many problems when we dealt with Newton's laws saying that the direction of the acceleration should be our positive x direction. So we are going to choose positive x to be towards the center of our circular path always. So that means that we're then going to be able to write, okay, my net force is equal to mass times acceleration, right? That's just Newton's laws. My net force in this case is my static friction force. That's got to equal mass times v squared over r. My static friction force is the coefficient of static friction times the normal force. I'll just copy mv squared over r down there. The coefficient times the normal force. But my normal force, and we're on a flat ground, level ground, so we have just mg for my normal force. So we'll carry this guy on over here. So we've got my coefficient of static friction times the mass of my car times g is equal to mv squared over r, which means solving for v, we see my masses don't matter. Solving for v is going to give me my coefficient of static friction times g times r, and I'm going to take the square root of that. We were told that our coefficient was 0.4, our radius is 150 meters. When we solve that, we get a speed of 24.2 meters per second. 24.2 meters per second, which comes to, I don't know, highway speeds. I think it's 53 miles an hour or so, which makes some sense. Let's do one more problem that just looks a little bit different. We still have uniform circular motion. For a hammer throw, so this is the exciting track and field event where you have the massive sphere on the end of something like a chain. We'll see in this problem why it needs to be a chain and why it's not a typical string or rope. We zing it around and around and around, and then we let go and it goes flying off onto the field. So we are told the mass of the hammer, 7.3 kilograms, and we are told the length of the chain. And if we're saying that we have a world-class athlete spinning it at 29 meters per second, we want to know what the tension in the chain is, under the assumption that the horizontal circle is centered on the end of the chain. So if we were to draw sort of a top-down view, I'll zoom in here so that I have a little bit of an isolated view. Here's my circle, and I've just got my hammer going around and around and around with a velocity v. So I know that this has a radius r, and therefore my force that's going to be directed on my hammer will be in towards the center of the circle. So the free body diagram for this object, let me just clear all this off the screen. My free body diagram for that mass as I go around, let's make this my circular path here. I've got my mass here. I'm just going to say that I've got my tension in my chain, what I'm going to call F of t, in towards the center of the circle. And we're looking down on this horizontal circle. You might say, well, don't I have a weight force directed down? Let's just work this problem as though the tension is the only force acting on it. You'll see why we can make that assumption once we're all done. So we will again choose positive x to be in the direction towards the center of the circle, which means that my tension force is positive in towards the center of the circle, and I can apply Newton's laws thusly. I can say my tension force is equal to mass times my centripetal acceleration, v squared over r. I am told my mass, right, in this problem it's just a direct calculation, I'm told my mass is 7.3 kilograms. My v squared is 29 meters per second. And then my radius I was told was 1.2 meters. When I calculate that out, I get 5,120 newtons. That comes to about, I don't know, 1,200 pounds or something like that. This is why they use a chain and not a wimpy little rope. 5,120 newtons. If I were to take, I didn't calculate it, give me a second, 7.3 kilograms times 9.8, the weight of this 7.3 kilogram mass comes out to 71 newtons. So my free body diagram in 2 dimensions, knowing that this is my tension force, would probably look something like, let's see, if I drew that tension force, let's see if I can draw a straight line. My tension force in towards the center, that's even worse. My tension force, good enough. My tension force in, that would be Ft. If that's 5,000, let's see, I take 5,120 and I divide by, what did I say, 71, something like that. I've got to draw something 71 times smaller. So let's see, I lost it now. I'm trying to zoom in. 71 times smaller, so maybe my weight is like that. Let's do it in an arrow that we can see. All right, I'm just making the point that here is, everyone see that? There's my weight down to scale, right? So that my weight is 71 times smaller than my tension. That's why I could ignore it. If I've got something in a horizontal circle like we did in lab, if we had a truly flat horizontal circle going fast enough with those rubber stoppers in lab, we can usually just neglect the downward weight because that tension force is so much bigger. That's just the net force. Really, my net force, is angled down just a little bit, but we're often just ignore it because it's so much bigger than our weight. So there's 2 simple examples for centripetal force. The big idea is that for centripetal force, when we have uniform circular motion, my centripetal force is in towards the center of the circle, and then when applying Newton's laws like we did down here, I choose the center of the circle, the direction towards the center of the circle as the positive x direction. That just gives me positive signs everywhere. So we'll see in class a few more examples of cars going over hills and under in a valley and stuff like that. We'll always choose towards the center of my circular path as positive x.